Hello and welcome back to the Artificial Intelligence Masterclass. In today's tutorial, we're talking about the intuition of why we need recurrent neural nets and mixture density networks in our full world model. Very exciting tutorial and a very exciting section coming up ahead. Let's jump straight into it. So here we've got our worldmodels.github.io, the website where we get all the information on the full world model that we're building. And today I wanted to start off by talking about this image over here. So the authors very eloquently draw the analogy between artificial neural networks and how a human plays baseball. So the thing about baseball is that the speed at which a baseball travels in the professional leagues or when a professional baseball pitcher throws it is very fast. Some fastballs can travel as fast as we can see here, 105 miles per hour. That's over 150 kilometers per hour. Now the distance between the baseball pitcher and batter is 60 feet 6 inches. If you're in Europe, then that is about 18.4 meters. Now, as you can imagine, that's pretty fast. In fact, if we take 18.44 meters and divide that by 169 kilometers per hour, which is 169,000 meters per hour, we'll get this many hours multiplied by 3,600 seconds in an hour. That's how much we get. So 0.39 seconds to react to a fastball in professional baseball. Now, the average human reaction time to visual stimulus is about 0.25 seconds. So even though we have a bit of time here, this is a bit more than we need to react visually, we still need to throw the bat. The thing about baseball is you don't just dodge the ball, you actually have to hit the ball. So you gotta whack the bat, which is not that light. You don't have that much time left to send a signal from your brain to your arms to whack the bat and hit the ball. So the comment that the authors make here is that actually baseball players, the only way they can hit a fastball is if they start swinging before the ball is actually thrown. And therefore what they're relying on is their prediction of the future, their prediction of what's going to happen, and that's what they're using in their action. And that's exactly what we want to implement in our artificial neural network, in our artificial intelligence. And the way to do that is to combine two new components that we haven't talked about before, and those are the recurrent neural networks and the mixture density network. So here we see a visual representation of that. So we've talked about recurrent neural networks conceptually, but we haven't used them in the model yet. So the way we're going to be using them is we're going to leverage recurrent neural networks to have a short-term memory of what's going on in the surroundings. So as our artificial intelligence is going through an environment and performing certain actions, it will always keep itself up to date of what was the previous state in which it was, in which it had been operating. So here you can see that the recurrent neural network is feeding into itself. So this is the recurrent neural network at point, like at the previous point in time. As an output, it has an output that's going up over here. We'll talk about that in a second. But also it's outputting this hidden value into its next state. So it's passing information. This is the memory part. This is the memory cell. Information is going from this previous state into the current state. And then after the current state is, all the calculations are done, not only will it output some values, it will pass information into the next state and so on. So that way it keeps this memory. So basically it can look at what has been happening to make the prediction. So for instance, once we get here, it will be able to make this prediction based on all of these things. So the question is, why is that important, right? So we looked at the baseball player. In baseball, you look at the batter, look at the pitcher, and you can see them running. And so you can calculate that. So they're running, and you can calculate that they're going to throw. Like over here, they're going to throw. So you can already predict that early on, and you can anticipate their throw. But you need the past information for that, right? Just by looking at the baseball player, at the baseball pitcher, it'll be quite hard to predict exactly when they're going to throw. I have an even clearer example for you. Let's have a look at this sentence. Can you predict the next word here? So this is your whole sentence. It says for, what's the next word? Very hard to predict, right? But if I gave you the words that came before this, with this word in the sentence, the words were too cool for. So now it's much easier, if you know the saying, too cool for school, to predict that most likely the word here is school. So we need information from the past in order to predict the future. We can't just look at the current state to predict the future. We also need information from the past, and that's where the recurrent neural network comes into play. Now, the question is, what is this mixture density network? Now, we'll talk about mixture density networks in this section in the following tutorial. But for now, what we want to understand is that the mixture density network is necessary for us here in order to make a non-deterministic prediction. We don't want to just say, all right, this is exactly what's going to happen, because we don't know for sure. We want to make a prediction that has a probability distribution. So every time here, what the mixture density network is adding to a model is, instead of, so here we have that latent vector that comes from our variational autoencoder, and what we're trying to do is we're trying to predict the next latent vector. So here at Z, we have the input of zt minus 1 plus the action that we played. So we want to now predict what will the next vector be. What will the next state of the environment be like? And then next time we actually have this value, we have the state of the environment. Now we want to predict what will be the next state of the environment, and so on. So we want to predict the state of the environment, but we don't want to just predict what exactly will the state be. We want to predict the distribution of states, so then we can sample from that distribution and train our neural network on different possibilities of what might happen in the future. And that gives our neural network additional flexibility, additional room for learning. So now, in a way, if we look at the combination of the two, we can see that the variational autoencoder, which we have here, which we already talked about, it is the spatial representation. It is space. It deals with how the environment looks and what the space can potentially look like. It gives us many different options of what the environment might be like through that latent vector and how we mapped it onto a distribution. Whereas the MDN RNN, it gives us options and different variations of time, how the future can look like, what different things might happen in the future. So together they model space-time. This is space, this is time, and both of them have distributions. They have they're non-deterministic. The way we built them, they're non-deterministic, and therefore they're giving us different possibilities of space and time, and that is allowing us to train our neural network even better. It's a very, very cool concept if you think about it that way, through space and time. And to finish off this tutorial, we have some examples here for the MDN component. So this is for the VAE, which we've talked about already. So for the MDN component, here we've got the V model only, so the variational autoencoder model only. As you can see, the car is driving very, it's kind of like jerky from left to right, and it's missing these sharp corners. But now, once we add a MDN RNN to it, so model M on top of model V, you can see the result is much smoother. So it's not as shaky, it's not as wobbly, and at the same time, it can better take these sharp corners because it can predict the future, what's happening in the future. So on that note, I hope you enjoyed today's tutorial. I look forward to seeing you in the rest of this course, and until then, happy analyzing.